Hello, today we will be looking at sketching graphs of rational functions. As always, we will go over a few tips and tricks that will allow us to simplify the problem, and then we will go into a few examples to test out what we've learned. This video will use concepts from identifying vertical and horizontal asymptotes, as well as solving for oblique asymptotes. If you need a refresher, I will link a few videos in the description below. I would recommend that if you're not comfortable in determining what your vertical, horizontal, or oblique asymptotes are, please check out those videos first and then come back to this one. But if you're good to go, then let's jump straight into it. When graphing rational functions, there are 6 main steps that we need to look at, and then I've added in an extra note that we want to make sure that we are aware of before we go into graphing. First, you want to look for oblique asymptotes and confirm whether they exist or don't exist, because you will need to remember to do those and solve for those in the problem. Next, you're finding all of your zeros in the numerator. Step 2 is you're going to find all of your zeros of the denominator, which are your vertical asymptotes. Step 3, find f of 0. So you're going to find the y-intercept if it exists, and then you're going to plot that. Step 4, you're going to find horizontal asymptotes, as well as any open circles that could exist in the graph. Step 5, you're going to find if the graph intercepts any of those horizontal asymptotes. And then step 6, you're going to sketch the graph. I do want to note that graphs of rational functions may become increasingly complicated as the degrees of the polynomials in the numerator and the denominator increase. Techniques in calculus or having a graphing calculator are very helpful of achieving a more thorough answer in the graph. And so because in today's examples we're not going to use a graphing calculator, we're going to do everything by hand, the graphs will be approximate and they won't be exact. For example, if we're looking at a parabola, we might not actually find its vertex in these problems, and that's where a graphing calculator or calculus will be very helpful. But for this video, we're learning the concepts and constructing a graph that's very, very close to what it is. It just might not be exact. So with that, let's get into our first example. All right, looking at our first problem, we have the function x plus 2 squared divided by x plus 1 multiplied by x plus 2. We see that this is already given to us in factored form, so there's nothing really we need to do. If we wanted to, we could further simplify this to x plus 2 multiplied by x plus 2 divided by x plus 1 multiplied by x plus 2. When we write it out this way, we can already see that we'll have a whole because we have the same function in the numerator and denominator, that x plus 2. We know that that's going to be a whole, but we will get there. Looking at our steps, it says as our first note to look for oblique asymptotes. And that again just states that the numerator is 1 degree higher than the denominator. In this case, they are the same, so there are no oblique asymptotes. For step 1, it says to find the zeros of the numerator or our x-intercepts. What we need to do is to set the factors of the numerator equal to 0. So we have x plus 2 with a multiplicity of 2. We only need to do it once, so x plus 2 equals 0. When we solve for x, we get x equals negative 2. For the information that we know now, let's plot this point. So at 0 is x of negative 2. For step 2, we're going to find the zeros of the denominator. The zeros of the denominator will tell us what our vertical asymptotes are. If we do x plus 1 equals 0 and we do x plus 2 equals 0, then we get x equals negative 1 and we get x equals negative 2. What we know here for that vertical asymptote is that negative 2, we've already plotted that, but because we're able to reduce this original function down to x plus 2 divided by x plus 1 by canceling out the x plus 2 in both the numerator and the denominator, then we know that there will be a whole at this point because it can't exist because you can't have 0 in the denominator. When you reduce the original function into what we have here, then by inputting that -2 into your value of x, you're able to see exactly where this point is actually going to lie, if it is going to be on that x-intercept or if it's not going to be on that x-intercept. When we plug in a -2 for x, we're going to get -2 minus 2, and we're going to get -2 plus 1. In this case, we see we have 0 divided by -1, which is equal to 0, which then confirms that this was in fact our x-intercept if it exists. However, because in the original function we can't have a -2 in the denominator, that actually becomes an open circle instead of a closed circle. And lastly, we still need to plot our x minus 1 because that is still our vertical asymptote. Now step 3 says to find if f of 0 exists. When we plug in 0 into our original function for all our x values, we're going to get 2 on the top squared and divide that by 1 multiplied by 2. This gives us 4 divided by 2, which is equal to 2. So at f of 0, we're going to get a value of 2. So we're going to plot that. If we go f of 0, we will go up 1, 2, and this is where our point's going to be. Next, it says for step 4, find any horizontal asymptotes, and if you haven't already, any open circles. So we've already found if this problem has open circles, and next what we want to do is find that horizontal asymptote. With our rules for horizontal asymptotes, we know that the numerator's highest degree equals the denominator's highest degree. When they're equal, all you need to do is take the leading coefficient of the highest degree in the numerator and you divide it by the highest leading coefficient of the number in the denominator. And in this problem, the highest leading coefficient will be 1, and we're going to divide that by the denominator's highest leading coefficient, which is also going to be 1. What we did to get there, if you FOIL the numerator together, you're going to get x squared plus 4x plus 4. The coefficient out in front of x squared is 1, and that is how we get our highest leading coefficient. And we're going to do the exact same thing in the denominator, which is going to be equal to 1. So that's how we got that. And 1 divided by 1 is equal to 1. And this tells us for our horizontal asymptote, y equals 1. When we plot our horizontal asymptote, then we just need to go through 1 to show that. Next, we move into step 5. And step 5 asks us to find if the graph intersects the horizontal asymptote. So what we want to know is when or if does the original function equal a value of 1. If we set the function equal to 1, so 1 equals x plus 2 squared divided by x plus 1 multiplied by x plus 2. If we further simplify this like we did up top, we're going to get x plus 2 multiplied by x plus 2. Then we're going to divide that by x plus 1, and we have x plus 2. We can cross these out because they are the same, and we're going to be left with x plus 2 divided by x plus 1, and we are setting that equal to 1 because we're trying to see if it crosses that horizontal asymptote, which means it needs to be equal to a value of 1. When we simplify, then we get x plus 2, and we move this x plus 1 to the other side by multiplying. We get x plus 1. The x's cancel out because they are the same. If we subtract an x from both sides, then it's just going to leave us with 2 equals 1. And this is not true because 2 does not equal 1, and therefore we know that it does not cross that horizontal asymptote. So then that gives us our bounds, and we cannot cross over this horizontal asymptote that we found or this vertical asymptote that we found. Now again, we are not using a calculator and we're not using calculus, and so this is going to be an approximated graph. However, from what we understand from the points that we have, all we need to do is plug in a few numbers to try to get us to an answer. If we start in this quadrant here, we already know, again, that the point 0, 2 exists, and it's bounded by this area here. So if we want to, all we need to do is find in a couple points and then sketch the graph. We use the original function at a value of 10. Knowing that we can simplify down to this, that's what we're going to do. So we're going to say 10 plus 2 divided by 10 plus 1, and that's equal to 12 divided by 11. And that is going to be equal to 1.09 or something like that, which then tells us at 10, this is going to be 1.09, which is really, really close to this line here. Being that we have 2 points, we know that it's going to go in this direction and it can't cross that line, and then it's going to continue in this direction. If you want to, you can plug in additional numbers to try to find points here. Because we have this bounded area and no oblique asymptotes, we can safely assume that it's going to follow this direction. However, if you are uncomfortable, again, just find additional points and you'll see that it goes in this direction, but never touches -1. So if you plug in f of -0.5, for example, that's going to get you very, very close to this line at -1, but we'll never touch it. Similarly, we need to find points down in this quadrant to figure out what the graph is going to look like. We already know that the graph is going to approach -2, but will never actually touch -2. But to see where the graph is, if we choose a value of -10, and instead of f of 10, we use f of -10, then we're going to get a -8 here, and we're going to get a -9 here. That's going to be a positive value, and it's going to be very, very close to 1, but it won't touch 1, which is what we have as our horizontal asymptote. It's going to connect to this, and it's going to go closer and closer to 1 this way. And similarly, if we use a value of -1.5, for example, we will get a point that's somewhere around here, and then we'll be able to connect these. And this is our graph right here. We see down here in this quadrant that we have satisfied the open circle, and we are within our limits of those asymptotes. And then in this section up here, there are no open circles, but we are still in that limit of those asymptotes. All right, let's look at another example. Okay, the next problem is a function x minus 1 divided by the quantity x cubed minus 4x. And the problem asks us to sketch out the graph. What we first want to do is just factor out to get it down to the least common term so we can more easily work with the problem. So if we factor this out, then we're just going to be left with x minus 1 up top, and then on the bottom we can take out that x, and then we're left with x squared minus 4. From there we know that that can further reduce down to x minus 1 still on top, x, and then we have x minus 2, x plus 2. And if we want to check x times x, x squared, -2 plus 2x, that gives us a 0, and then -2 times 2 is -4, so that's the same. Looking at our steps, it says for our note, look for any oblique asymptotes. Again, the numerator is not 1 degree higher than the denominator, so we don't have any oblique asymptotes. Next, we look at step 1, which is find the zeros of the numerator, or our X-intercept. So at step 1, we just find the zeros. So we set x minus 1 equal to 0, and x is equal to 1, and that is going to be the first point on our graph. And x equals 1, and we will put a point there to show our x-intercepts. Next, what we want to do is to find our zeros of the denominator to find our vertical asymptotes. So we see we're going to have three different zeros. We're going to have an x equals 0. We're going to have an x minus 2 equals 0. And we're going to have an x plus 2 equals 0. Now we don't have to worry about any holes here just because there are no common factors in the numerator and denominator. So that's one less thing we have to worry about. But we see at x equals 0, that is where one asymptote lies. So we'll draw in that line there. Next, what we want to do is solve for x here. So we get x equals 2, and then we're going to get x equals negative 2. If we graph that on our line, so we have negative 1, 2, and we have 1, 2 there. We sketch this here down as our asymptote, and we sketch this one down as our asymptote. Step 3 says to find f of 0 if it exists. We see that it's on one of our vertical asymptotes, so this will be a really good indication if it exists or not. Because it is an asymptote, we have a good feeling that it's not going to exist, but if we wanted to find it out, then we just would plug in f of 0, and if that's the case, it's going to give us 0 minus 1, which is negative 1 on top, but then in our x's we have that 0, and then we have a 0 minus negative 2, which is negative 2, and then 0 plus 2, which is positive 2, and this is equal to negative 1 over 0, which is undefined, so it does not exist. Which again, we kind of figured because it is already on a vertical asymptote. Step 4, we go for horizontal asymptotes. Well, in this case, we know that the numerator is less than our denominator. And when the numerator is less than the denominator, then we know that the y equals 0 is our asymptote, is our horizontal asymptote. So we can draw that in. Step 5, we want to see if the graph intercepts our horizontal asymptote. So to do that, we know that y equals 0 is our asymptote. If we set our equation equal to 0 and solve, then we get 0 equals x minus 1 divided by our denominator, x multiplied by x minus 2 multiplied by x plus 2. When we move all of this over to the right hand side, then we get 0 equals x minus 1. And when we solve, then we get x equals 1. We know that it only crosses the asymptote at the point x equals 1. The point that we have drawn already at 0, 1, we'll know that we'll actually go through that horizontal asymptote. However, that's the only region in the graph that will cross the asymptote. So for part 6, all we need to do is sketch the function. All we need to figure out is if it's above or below the graph. Let's plug in, for example, a positive value. Let's just choose 10. Why not, to see what we get? So if we do f of 10 and we plug that into the numerator, then we're going to get 10 minus 1. And if we plug that into the denominator, we're going to get 10 cubed, which is 1,000, and then minus 40. And this is going to be equal to a 9 divided by a positive number, 960. So we know that this is positive, which means we know it's above that asymptote. Next, we also know that at that 10 value that we just found, that's going to be, it's really, really close to 0. So it's going to be somewhere down here in this area. And if we wanted to, again, solve for additional values, we can go a little bit closer. We know that this is 2. So if we did 3, for example, if we plug in f of 3, then we're going to get a 2 up top, and we're going to get 3 cubed, which is 27, and then minus 12. So that's still a positive number. So we know now that if we go closer to 3, then we're still going to get 2 divided by a number, which is still positive, which then puts us about right here. Again, we can't cross these axes, so we know that the graph is going to look something like this, bounded by those asymptotes. Now if we look at the next column over, we already know that value f of 1 is 0. Now we just need to figure out if it's going up or down. And so with that, we can plug in a 0.5 or a 1.5 because we are bounded by these asymptotes. And so if we plug in 0.5 into the function, then we're going to get a negative 0.5 up top, and we're going to get 0.5 cubed minus 2. So that's going to also give us a negative number because 0.5 cubed is 0.25. 0.25 times 0.5 is 1.25 minus 2. That's a negative number. A negative divided by a negative is a positive. So we know that f of 0.5 is positive. So we can draw that line there. And if we go f of 1.5, then we're going to get a positive number up here, up top, and then 1.5 cubed is going to give us 3.3 something, and then we have minus 1.5 times negative 4, which is going to be 6. So that's a negative value. So we have a positive divided by a negative, and therefore we know that it's down here. And that means that this graph goes next to these asymptotes, but again, never cross the line. And it also contains this point, 1, 0, and that's that segment. We continue this process. So if we move into the next segment, we know that negative 1 exists in here. So if we plug in a negative 1, we're going to get a negative 2. Negative 2 divided by negative 1 cubed is a negative 1 minus 4 times negative 1 is a positive 4. So we get negative 2 divided by 3, and that is a negative. So we know that the point will be down here. And then going to the left and right, similar to what we did previously, if we do a negative 1.5, then we're going to get a negative 2.5 in the denominator. We're going to get, again, that 3.3 value down here, but that's going to be negative as well. And then we're also going to get negative 4 times that negative 1.5 is going to give us a negative 6, but it's really a positive 6. So that's really a negative in the numerator divided by a positive in the denominator. So we know that it's going to go down this way. And similarly, if we plug in that negative 0.5, it's going to be essentially what we just did over here. So we also know that that's going to be negative as well. So that means this graph goes down here. And then lastly, we look at our last quadrant, and instead of doing the positive 10, if we do a negative 10, we'll see that it goes out close to this line. And we'll see that it also comes up close to this line if we do a value close to 2. And this is our graph. Again, because we don't have a calculator or we're not using calculus, it is approximated. However, by plugging in values around the points in the quadrants that have our set limits, we're able to deduce what the graph is going to look like. All right, let's look at one last example. In this problem, we have given information. So we're given the vertical asymptote, x equals negative 3 and x equals 1. We have a horizontal asymptote at y equals 0. We have an x-intercept at negative 1. We're also given that the function at 0, or the y-intercept, is equal to negative 2. And then we're also given that there's a hole in this problem at x equals 2. And the problem asks to find an equation of a rational function that satisfies the given condition. So with this problem, we're going to be working in reverse. And all we need to do is just understand the rules of asymptotes and our graphs that we've looked at to be able to solve this problem. We know automatically that for vertical asymptotes, we're going to be looking at the denominator of the problem. So if we have f of x, and we're talking specifically about the vertical asymptotes, we know that if there's one at x equals -3, then we have the value x plus 3 here in the denominator, and we also have the value of x minus 1. If we take these values in the denominator, x plus 3, set it equal to 0 to find that vertical asymptote, then it would be x equals -3, which is what's given right here. And similarly, if we have the x minus 1, we set that equal to 0, then x would equal 1, which is what we're given right here. So now we know two terms in the denominator of this function. Looking at the next set of information, we have the horizontal asymptote. Now, a horizontal asymptote, in this case, y equals 0. We know that when y equals 0, the exponent in the numerator is one less degree than the exponent in the denominator. And that's by our laws or by our rules of horizontal asymptotes. So if the exponent in the numerator is less than the exponent in the denominator, then your asymptote is equal to 0. Again, we know that the numerator is going to be a lesser degree than the denominator, so that's something that we just need to pay attention to. Next, what we need is the x-intercept. Well, the x-intercept we know is in the numerator. So with the numerator, with x-intercept, then we know that we have the x plus 1. Again, if we set that equal to 0, then we're going to get the x minus 1, which is what we're given right here. And we also know that there's a hole at x equals 2. So at x equals 2, that tells us at a hole that there is a common factor in the numerator and the denominator, and that common factor is going to be x minus 2, because if we set x minus 2 equal to 0, x would be equal to 2, which is what it stated right there, and we have to make sure that we plug that in to the denominator as well. Now we have a degree polynomial at the top of x squared, so we have a degree of 2, and we have a degree in the denominator of x cubed. So now we've completely satisfied this statement right here, and that is accurate. The last thing we need to solve for is when f of 0 equals -2. To do that, all we need to do is plug in 0 for x and manipulate the problem to figure out how we're going to equal -2. If the function is at 0, then we have 0 top plus 1, we have 0 minus 2, we have 0 plus 3, we have 0 minus 1, and we also have 0 minus 2. And again, this has to equal a -2. In this case, we simplify, we get 1 multiplied by -2, and we get 3 multiplied by -1 multiplied by a -2. We get -2 divided by a +6, which is equal to a -1 divided by 3. And we're trying to get this equal to a -2. So how do we do that? If we multiplied this left side here by a 6, then we would have -6 over 3, which is actually equal to our -2, which is exactly what we're looking for. Therefore, we know that if we multiply the numerator by 6, then we're going to get the value of -2. So we plug in 6 out here in front, and that will satisfy this term here. If we wanted to check our work, again, now we have the function f of x equals 6 multiplied by x plus 1 multiplied by x minus 2 divided by x plus 3 multiplied by x minus 1 multiplied by x minus 2. If we're solving in 0 here, and now we have the 6 that's out in front, everything stays the same, except when we get into this step, instead of it being -2, it's going to be that -12. -12 divided by 6 reduces down here, which is actually that -2 that we were looking for. And again, all of these values that were given are satisfied, and therefore this is our equation. If you truly understand how to find your vertical asymptotes, your horizontal asymptotes, your x-intercepts, and any holes in the equation, then you'll be able to execute this problem. And there you go. Now you understand how to sketch graphs of rational functions, and or if given information, how to find an equation based off the information given. If you have any questions, please leave them in the comments below. If you learned something, please like and subscribe, and we'll see you next time.